Hello, Marco Provitali. I'm here to present the work carried out by my colleague Insue on the PFEM simulation of the downward trapdoor problem. So, the trapdoor problem is a classic physical model used to quantify the stress and strain distribution in granular material above a yielding trapdoor, with practical application mostly concentrated on tunnel excavation and sinkhole formation. The main issue of simulating this kind of problem is that the formation of the sinkhole develops or creates large displacement in the material, which cannot be simulated by traditional continuum analysis methods due to mesh distortion. For example, you can see one very old example in which the nodal or the formation is imposed as nodal displacement, the other in which uh, moving boundary is improved or employed, but still this uses very minimal trapdoor formation or deformation. So here the vertical deformation is 8% of the lateral width of the boundary for the moving trapdoor, while what you're trying to achieve here is simulating or replicating the experimental test carried out by Kikumoto in 2004 using 2D apparatus and simulating it with a 2D plane strain model, well, basically using the same dimensions and going up to a trapdoor displacement to diameter of 0.4 instead of 8%. So how is this done? The numerical framework for PFEM, it can be simple or can be described as follows. You solve the classical finite element equations using incremental finite elements. Then you apply the node displacement and let the nodes move according to the increment in time step. And then you delete the connectivity matrix and you obtain a cloud of particles. Then this cloud of particles is first identified using a convex hull approach, and then it's refined using an alpha shape approach, which you can see on the top. So first you identify the boundary and then you refine it based on the distance between each point so that you only select the points that belong to the boundary to identify the domain. And finally, the new domain is just recreated using Taylor triangulation. One important aspect of this is that since the connectivity matrix is not kept, the deformation of each individual element is not kept, but it's then recalculated using, or it's not calculated, but it's passed, the geometric deformation is passed as an approximation of the Jacobian of the deformation gradient before deleting the connectivity matrix, while the deviatoric portion is then obtained from the displacement, which is also stored at the nodal position. Then this approach is also further enriched by considering contacts between the wall and the mesh. In this case, we're using a rigid wall, meaning the shape of the wall is approximated with a function, making it very easy to compute or to detect contacts. Just if you evaluate a function for each node position, depending on the value which is greater than 0 or less than 0, you get whether a point is inside the wall, and then if it's inside, you just apply a repulsive force depending on the conjunction from the surface to the mesh. Then, since the material can have significant plastic straining, non-local regularization is used to obtain a mesh independent result. And then we're using a target element target distance equal to 6% of the diameter of the trapdoor or the size of the trapdoor. And finally, due to as well to improve the quality of the result, to make it more efficient while not creating a mesh dependency, we're using H adaptivity based on a threshold of the plastic deformation. So results, earth pressure, you have at the initial state, you have here we're plotting the stress eigenvectors at the beginning. So first eigenvector is black, the principal eigenvector is black, secondary is red. And initially you have a uniform state with vertical eigenvector, and then as the trapdoor moves, you have this creation of arching that lowers the load on, well, just above the interface or just on the edge of the moving trapdoor, keeping a constant or more or less constant value of stress on the rest of the trapdoor and increasing the stress acting on the edge of the stationary zone. So this is being calculated and compared with the experimental data produced by Kakumoto. Here you can see that the results match more or less the experimental values for the displacement. Delta is the trapdoor displacement considered, while these values keep more or less constant during the entire process. While on the left here you have the loosening earth pressure, so how much the earth pressure changes from compared to the initial state, and you can see that the results capture quantitatively the trend. There is one difference toward the end, which we will go on to discuss later on. Then why was there this difference? It's probably due to the different surface settlement. You can see that as the trapdoor moves downward, the deviatoric strain stops being concentrated into a narrow band and develops into a wider fan shape or wedge shape. And while this is shown here with the continuous black dotted line, the experimental results show a much smoother interface, which is what I assume is the reason for the not perfect capture of the loosening of earth pressure during the surface settlement. And then if we measure the ground movement, so total ground movement or absolute value of ground movement divided by the trapdoor displacement, considering a shallow embedment, you have at the very beginning just the formation of this well, displacement map, while afterwards the displacement becomes very localized, as you also showed before with the deviatoric plastic strain. And then this continues to be more or less constant until 12% of the trapdoor size. So here, first you have very vertical at the very beginning, and then after a certain displacement, the mechanism changes significantly. It becomes a wider wedge shape, which creates this also very different surface above. What happens? So how can you see this? Also after the 3 millimeters, you have the formation of or the widening of this fan and the uniform slope deformation in the finite or the experimental, while this is not uniform, or you have a sigmoid slope, which we assume is due to the discretization of the uh, particles in the experiment and the difference with the continuous modeling done here. Conclusions, PFEM is applicable to this kind of large strain information, offer the advantage of simplifying the modeling because we can apply larger displacement. The simulation results match the experiment result surprisingly well for surface statement, low distribution, and temporal changes, while for large displacement, the uh, overall mechanism changes significantly, which means it's necessary to, or using this large deformation numerical modeling becomes much more important than for low deformations. And so this method should be used in the future to investigate tunnel excavation. Well, thank you for your attention.